Hello everyone. Thank you so much, Chandan sir, Janikram sir, Sanket sir, Ravindra sir, and Sharayu. So let me go ahead and share my screen. And so I would like to explain the format of hackathon like we normally do. Like people who have recently joined, these hackathons are a revision of the actual lecture that has been delivered by the primary faculty. Here for blockchain, this is Professor Panduragan sir. So every hackathon, we revise a portion of the concept that was covered by Professor Panduragan sir, right? So if at all you have recently joined, you can choose to be part of the session or start from the beginning and kind of reach out to the current status, the current state of the revision hackathon, or you can choose to continue with your learning. And these hackathons happen in cyclic fashion. So first, right now today we are in the sixth module. So as we proceed forward, once we finish 10 and solidity, then we'll begin from the start, right? So I hope that is clear. Okay, so let me go ahead and share my screen and point you in the direction of what we are covering today. Okay, this is my screen. So once you open your Teachable, this is how your Teachable will look like. And in this, today we are covering the module 6. The portion of the module 6 we have already started and finished, completed in our previous session, right? Okay, so we have finished in our revision hackathons from the beginning, and we have completed all of these modules. And now we are discussing the module 6, where we have previously spoken about the n-lock time and all. Today we are going to cover the more about the block header and the Merkle root, right? So now let me go ahead and kindly quickly do a quick recap of what we've done previously, right? So in our previous session, what we have done is we have understood, in a very previous session, we have understood and examined each of the transactions, and we have understood the inputs and outputs in a transaction, and we have seen in detail of how these inputs and outputs are stacked, and how there is a better way than directly using the public key hash. If at all you are trying to send it to a person, how can you make it in a way that you do not lose the Bitcoin that you have sent? So where we have discussed about the pay to public key hash, and we have also understood the problems that come with the pay to public key hash, right? For example, when A is transferring to B, if B is no more, or B has lost access to their key, whatever money you have sent is lost. So in that case, what you can do is you can send this to a multi-signatured approach, where A, along with 2 or 3 more people, might be making one public key, right? So basically, this is how it will go. So this is called M out of N signature scheme. So for example, A along with B and C are together making one single public key hash, right? So this collectively generated public key is called a script, right? So this unlocking script has to be specified in that particular signature. So how this works is, for example, if I am trying to send it to this particular one single unlocking script, which consists of 3 scripts, 3 public keys within. So what we are going to do is this, whenever you are trying to send, it will check if any of the M out of these N, like for example, if you specify in an example like this. So the sig verify is a command in the script language of blockchain. So it will check if 2 out of these 3 signatures are matching, then you will be able to send the Bitcoin to that particular person, right? So this N could be till 15. It can start from, like, for example, if you specified 3 out of 15 and use the command check multi-sig, then the sig verify will check if it has 3 signatures out of all the 15 or 10 that were initially declared. And if that is true, it is going to go ahead and send the Bitcoin. So this is what we have discussed previously. Okay, so basically, Chandan sir, if this is your first session, so how I would request you to go forward is, like, you can get started from the beginning, right? So if you're able to access your Teachable, you can start from the module 0, then go for the module 2. Like, so it is very simple. So if you go ahead and start any of your Teachable module, so you'll be able to see a private video that is only available for you, and you can start with the lecture and make notes, right? So if at all you want to go through the revision hackathon of the same lecture, the revision hackathon is available in your inner circle, right? So you might have had access to 4 lectures. So let me also share the inner circle. Okay, let me share my screen. Now, if you see this particular screen, so first way is to go access sequentially all the lectures at once. Or what you can do is, for example, if it is module 1, you go through this module 1's actual lecture by Professor Pandurangan, and then go through the revision hackathon of the same, right? So you can parallelly watch both of them, right? So the revision hackathon was a live session done regarding to the actual lecture. So these revision hackathons happen in a sequential manner. So if you face any specific challenge here, sir, you can always reach out. So that should not be a problem, right? So I hope this is clear, Chandan sir. So the inner circle link will be available on your Teachable account, sir, right? So if you go to, let me share this link, and right, so you can go on these particular session. I've just shared with you a link. So if you click on this particular link, which is LMS/courses and enrolled, it will show you 4 courses, whatever. Yes, sir. Okay, so people who have recently joined, I mean, just now joined, I request you to mute. Thank you. So I hope this is clear right now, sir. So if you access your Teachable, you'll be able to see all the inner circle and the actual lectures in your Teachable account. Thank you so much, sir. Right. So we're just recapping what we have learned in our previous sessions. So we have understood in detail about the check multisig, right? So if any of the one person's key is compromised, it can still be accessed, because you can still have any of the 2 keys out of the 3 matching, right? So that so money is never lost, and the N could be till 15. Right, so we have understood all of these, and we have understood the advantages of this, like, transaction bytes. Like, for example, instead of trying to send 15 people's public signatures or the signatures, scripts and keys together, you can directly hash it and send that in the transaction, right? So you can pay to, you can just specify and just send it to the script, and it will be easy for you to send the amount to that particular person. So the fee you pay also becomes lesser, because if you're trying to send transaction or the public keys of 15 people, it will be a bigger transaction length. But if at all you are sending the hash of all of these together, the fee you pay will also be lesser. So the transaction will take lesser storage on the block, and the fee that the miner will charge you will also be lesser. So in our previous session, we have seen the structure of the transaction, right? So every transaction has the version, the input counter, inputs, the output counter, outputs, and lock time. So we have understood these in our previous sessions also, but in the last session, we have understood these in a detailed fashion. For example, in the input, we have a few elements like say the previous transactions hash, the previous transactions index, the script length, and the signature script. So all these things, while we discussed inputs, we discussed at length, but in our previous session, we saw that each of this element has its own size, right, in bytes. So that was mentioned by the professor during the session. So similarly, output also has the Bitcoin value that you want to send, the length of the script, and the public key script, right? So these are all things that we have seen. So each of these mentioned elements takes some size on the transaction, and that is what was mentioned in a previous session, right? So you don't have to actually memorize these, but it is always good that you know that, okay, this is what each element occupies, this size occupied by each of the element in that particular transaction, right? So then after understanding each of the element, we understood n-log time, right? So we have understood n-log time by one reference. So let me go ahead and share that reference. Okay. Okay, so let me share my screen again. Great. So we have seen the definition of n-log time. Basically, n-log time is one of the parameters applied to each transaction. It is specified in two ways. One is the Unix time or the block height, right? So this is what we have understood previously. So like, for example, if the n-log time is less than 5 into 10 to the power of 8, then it will be unlocked, right? That block will be unlocked from the memory pool and validated after so and so length of the block. For example, we'll see that example here. And if it is greater than or equal to 5 into 10 power of 8, then it is being specified in Unix time, right? So you also understood what is the Unix time. So all the time, any timestamp in computer format is stored as Unix epoch time. For example, the current time, whatever is there in Unix time is this much. So which every passing second, the counter keeps updating, right? So for example, this particular timestamp, for example, if I'm going to change any of this, let's say I'm just going to make it 1000. And when I'm going to enter this, so it is going to be, it is today's date, February 28th, and in GMT, 10 hours, 43 minutes, 20 seconds AM, right? So in our time zone, it was 4:13 PM, right? So like every timestamp has one specific date and Unix time up, to it, right? For example, now if you have all zeros, so this is from where this timestamp is being calculated. So the zero Unix time was on January 1st of 1970, right? So in GMT, it is 12 AM. In our time zone, it was 5:30 AM, right? So this is 53 years ago. From there, the counter kept running, and this is where we are right now. So if at all nlock time is greater than 5 into 10 power of 8, that block will be verified after that timestamp. For example, if in a future timestamp we are doing it, like for example, if we say unlock my my block after, let's say I'm just going to make it random. I'm just going to say 8. So after unlock, the nlock time mentioned on that particular block was this number, which means I'm telling unlock that particular block after March 12, 2023, 12 hours, 32 minutes, 47 seconds, right? So this is what we have understood. If it is less than 5 into 10 power of 8, right, then unlock my block after one specific, after these many blocks have been verified, right? So let's see an example. Right? So for example, this number, if nlock time was 4,52,845, this meant unlock, the transaction could only be relayed onto the network after the blockchain reached a height of 4,52,845. If it is anything higher, it will consider it as an Unix time, right? So for example, here, going by the example, if you check, so it will be unlocked on May 12th, 2017, right? I hope this was clear in our previous sessions. So if this was clear, type C in the chat box. So people who are watching us on our social channels, and any members who are watching us on our YouTube or LinkedIn channels, you can use the comment section. Thank you, Janakiram sir. Thank you, Ravindra sir. Thank you, Prashant. Thank you, Sushil. Okay. So now what I'm going to do is I'm going to continue with today's portion, which is block header, right? So whenever a transaction is happening, right? So what happens is it has the series of transactions. For example, every block. Now we have discussed each input and output of each transaction. Now we have completed with the transactions. Then we entered the block. We understood what each of the block is there, what it is doing. So let me show this particular example that professor takes in the session. For example, there is one block of transaction. Every block has something called a header, right? So there are a lot of transactions. For example, every miner, whenever he takes a few transactions from the memory pool, he validates them and uploads them onto a block, right? So each block will be of 1 MB size, and how many ever transactions fit in that particular block, he's going to upload them, right? I mean, he is going to validate and add them to the block. So every block will have a header, which will tell us, what was the previous block it is connected to. So basically, now, if we try to decode the word blockchain, so each block which has transactions in it that was uploaded or validated by a miner connects to the previous block by the hash of that particular header, right? So let me go ahead and show it. Okay. Yeah, so now every block will have this way. So first there'll be this header of this particular block is going to have a block number and is going to have the hash of the previous block, right? So whatever the hash was there of the previous block will be added on this. So that is this is the one way how each block is connected to the previous block, right? So there are other things that are there in the header also, which are Merkle root, which we'll discuss today, and time, at what time the block was relayed, the bits and nouns, right? Nouns. So we are going to discuss nouns now, what is nouns in our upcoming session. But one thing that you need to understand is we have understood that every block will have a series of transactions, right, that are uploaded or validated by the miner. but it also has a header which has these elements, which is the block number, which is then what is the block number? If you have seen the block height, the number of the block number, right? So because if you have seen, we have checked the block 5 lakh, right? So if you remember, we have checked onto the screen and we have validated what all things are available in the block 5 lakh, right? So for the people who have just joined, I'm just going to share how we have done it. So it becomes a little easier for everyone. Great. Okay. I share my screen. So we have went onto this website called blockchain.com. Then we went into the Explorer. So because each of the transaction is transparent and is uploaded and is public, anyone can see what is contained in each block. So when you go to enter 5 lakh, so what we are doing is we are trying to check what is there in the block 5 lakh block, right? So in block 5 lakh. So this is the block number. So now in this particular, okay, so sometimes this doesn't properly open. So let me go ahead and refresh this once again. Or let me try a different block. This also happened previously once. Okay, so the 4, one less block than 5 lakh we have opened. Now, what happens is this is the block number, and in that block there are a lot of elements that you can see, right? So you can see that the block value is there, the what are inputs and the number of transactions. So now you can see that this particular block, which is 4,99,999 block, has 2,729 transactions in it, right? So those many transactions got added into it. So if at all we come back to our presentation, now you can see that there are, like, if we are considering this as the 4,99,999 block, that is the block number, and there are 2,700 change transactions in this particular block, right? So there's also the header, right? In that header, all these other inputs are there. So this is how we have seen, and we have validated in our previous session. You can go through the actual lecture by professor, or you can watch this in the revision hackathon also, where we have covered more in detail about each of the block, right? So the block number is there, and hash of the previous block is also there. So, and then the Merkle root is also there. So we'll understand is the Merkle root, what it is. So now when we say this is our block, if this is the new block, in this block, for example, this is the 5 lakh block, and this will be the 4,99,999 block. So this will have a hash pointer, which will be the hash of the previous block, right? So this will there'll be a hash of the previous block. So this is called the hash pointer. When you look at the blockchain, all of these blocks are not actually physically connected by a chain, right? So they are connected by the previous block's hash, and which is also known as chain, right? So these blocks are connected by the chains, which is a connect to the previous block. So this is also known as hash pointer. And how this works is whenever the actual pointer is there, so it is the hash of that particular block is added into the hash pointer. So hash meaning we are going to hash twice, right? So let me go ahead and share a little bit more inputs on this, right? So now normally what happens is whenever one particular hash is there, a hash will be of 32 bytes, and you're going to double hash it and upload, right? So this is what will be the hash. Now let me go ahead and try to break it down on what is this Merkle root. right? So if you have understood what the previous block's hash is, type Q in the chat box and how two blocks are connected, right? So if you understood how two blocks are connected, type U in the chat box. Thank you, Sharai. Thanks, Ravinder sir. Thank you, Janaki. Thank you, Prashant. So now we've understood this. Now let's try to understand Merkle root. So now we know that there are a series of transactions. Now, as we have so many transactions in that particular block, there is a way to have all this transaction identified by having one particular transaction. So which one particular root, we're going to understand about that. So now if you have gone through any of previous data structures concepts, Merkle tree is a term that you might have heard previously. So let me explain. For example, in this particular in this particular block, let's say there are these 4 transactions. We're talking about a series of transactions, right? So let's say in this block there are 4 transactions, right? So the transaction 1, transaction 2, 3 and 4 uploaded, validated by a miner and uploaded onto the block. So there'll be many, like we had 2700 change in one particular block. Similarly, let's say for example we have 4 here. So now what happens is each of the transaction first is concatenated with the other transaction. For example, transaction 1 is there and transaction 2 is there. So both the transaction IDs are concatenated or joined together and hashed, right? So when you hash them, one particular hash gets created, which is like, for example, this is 1 and 2. The hash will be hash 1, 2. And similarly, you create another hash, hash 3, 4, right? So you can see that you are able to create 4 hashes of this, right? So each transaction, for each transaction, you have a hash of each transaction, and then you're going to, club both of them and rehash, right? So for example, hash of 0 and 1 becomes hash 0, 1, hash of 2 and 3 here becomes hash 2, 3, right? So, pardon this, right? So, and then you will have hash 0, 1, 2, 3. So this particular, top hash, whichever is there, it is called the Merkle root, right? So whenever you have transactions, the series of transactions in the body, all the transaction, if you list, for example, there are n transactions, hash of each of these transactions is made. So there will be n hashes, and then each of them is clubbed into 2, concatenated into 2, and then rehashed. And like that, you reach to the top hash, right? So that particular final hash is called the Merkle root, right? So let me share one reference which will be helpful in trying to understand. While I go through this particular reference, I'm going to share it with all of you. So I've just added this onto the chat, right? So now, for example, let's say these are all the transactions. All of them first are hashed, and 2 together concatenated and hashed. And similarly, all of these, reach out to one single hash, and this becomes our Merkle root, right? So now what happens is, if you have even, right, this also is explained by Professor Pandurangan sir diagrammatically. We are going through references, right? So now if you see, if there are even number of transactions in the n number of transactions, it is easy to reach to the Merkle root, right? So you get hash of all the n transactions, then concatenate 2 of them, hash again, and get one level above, right? So this is how it happens. But what happens if it is an odd transaction, right? So if there are n transactions, and let's say those are odd, so what happens there is, so it is in detail explained here, but I'm just going to walk you through that process, right? So let me just go ahead and help myself here, right? So let's say you've reached, right? So whenever you have an unbalanced Merkle tree, or you have 5 transactions here, so what you do is you do hash of all of these, right? So you have 5 hashes, and the nth transaction, what you do is you duplicate the same, right? So you're going to duplicate the hash of the same, and then do on the above level hash of both of it, right? So for example, if there are 4 transactions, this is how it will go. Hash 1 2 it will happen, hash 3 4 will happen, hash 1 2 3 4 will happen. But if there are 5, so you're going to do first hash 1 2 hash 3 4 is there, then you're going to do hash 5 5, right? This is how it will go. So now after you do this, now you have let's just say 6 of them, 1 2 3 4 5 6. Now all of these are done, and now you have how many? 3 above. On the level above you have 3, hash 1 2 hash 3 4 hash 5 5. So now what do? You duplicate it once again, hash 5 5, and then this becomes hash 5 5 5 5, and this will become hash 1 2 3 4. So the Merkle root will have the hash of these both concatenated together, which is hash 1 2 3 4 5 5 5 5, right? So if you understood, first point is what is a Merkle root, which is nothing but all the transaction leveled up hash together, and the one in the top is called the Merkle root. If you have understood that, type U in the chat box. Right. Okay. So now this particular root, thank you so much, Anika, sir. Thank you, Rendra, sir. Thank you, Taslim. Thank you, Sharayu. So now this hash is included in your block header, right? So this is the Merkle root. You do not have all the hashes. You're going to have the Merkle root, right? So we'll see the benefits of this also. So now we've also understood how to handle the unbalanced Merkle, unbalanced number of transactions. So for example, if you have odd or uneven number of hashes, then this is how you're going to work with it, where you're going to duplicate whenever you find an odd number of hash or transactions, right? So this is how we do it. So now each of these transaction ends, the end transactions are called the nodes, and the hashes of each of these are called Merkle leaves, right? And because this is the Merkle root, whatever comes in between are the Merkle branches. So this is like additional information if you are interested to understand. This is the transactions, Merkle leaves, and Merkle branches, and the Merkle root, right? So now Professor Pandurangan also explains, for example, in this particular set, there are 4 transactions, right? 4 transactions. So how many levels of you have to go up for the Merkle root, right? So then the formula for that is n log 2. So let me go ahead and write it here. Okay. Log n, sorry, log n, and because I'll not be able to subscript it, so let me just try it. And okay, I was able to do it. So now n base 2, sorry, log n base 2. So now this is the number of levels, will be log n base 2. So if you understand logs, that is fine, but even it is very easy to calculate. So log calculator, you can go ahead and do. So for example, log 4 base 2, I'm just doing this. You will get the value here, but easier way would be a log calculator, and you can open any of it. So for example, log 4 base 2. So when you calculate, you can see that 2 levels, right? So now if you come to your reference to actually go to the Merkle root, when you had 4 transactions, you had to go 1 and 2 levels to reach your Merkle root. If at all there were, let's say, 8 transactions. Now, this is the example that professor draws in the session. So now how many levels it will be? It will be 3, right? So there'll be an additional level. Okay. So this is how you also know the number of levels that you have to go up, right? So these are a few things that we have understood about the Merkle root. So what are the benefits, right? So if you go through the reference that is shared, now what happens here is you can always add the Merkle root in a different way. Okay, so let me go ahead and show that. Yeah, so now do you really need Merkle trees to verify the block data? So the another way is do hash of all the transaction data concatenated together, right? So which is like transaction 1, 2, 3 and go till n. And if you do a hash of all of these, so that will also suffice for you to do, add as the, root transaction hash. But there's a challenge. So why do we do this extensive, Merkle level of root, right? So how do we do Merkle? Why do we do Merkle tree? Is the efficiency becomes better and also is good. It is good in validation. For example, now let's say the first use case is the immutability, right? So for example, you have 5 transactions here and someone instead of 4 changes the transaction or gives some other transaction, right? So somebody is trying to manipulate or tamper the block. So now what happens is when you add in one particular mistake or you add another data point here, now what will happen? So the Merkle, it has to go up because hashing, we've understood hashing in our previous sessions. So even if there's a smaller change, the output will change, right? So let me just go ahead and show you the new members if you're trying to understand this. So basically SHA-256 is the hashing algorithm. We discuss about it in detail. For example, there is any data like I'm just going to input any random text, for example, it's my country. Okay, so now if you see every input that is given has a very unique hash. Even if I make a very small change, like I'm going to say change y with I, the whole of the hash changes, right? So similarly, when you come here, if there's any change that happens, what will happen is the hash of both of those will not match the actual hash and the top Merkle root will change. So if any of single transaction is changed, the Merkle will change, right? So I mean the root will change. So because of that, you will know that some tampering was made in that particular block, right? So you might say that if you have a longer transaction, even if there is any change that happens in one portion, the hash will still change. But here you don't actually have to go and check all the transactions. If there is error in one transaction, you just have to match it with the other, and you can see within 3 steps you are able to know that this particular block data was tampered, right? So this is one of the top top cases of why we use a Merkle tree, because if you see the Merkle root will change if any of the transaction data is tampered. And when the Merkle root changes, it is immediately traced onto the blockchain environment, and others do not confirm or reject that particular block, right? So if this is understood, like why first use case of the Merkle root is to check if there's any tampering of data. If you understood that, type U in the chat box. Thank you, Janaki Ramsey. Thank you, Prashant. Thank you, Sujit. Thank you, Sharaya. Right. So now this is what is one benefit. The other benefit, which I've already explained while talking about it, is very efficient to check if a transaction is there in that particular block. So for example, if you are trying to check if one transaction is there, so you don't have to actually check all the transactions. You can check the number where that particular transaction is there, match it with, concatenate with the one adjacent to it, and see if that particular Merkle root is still being achieved. So if using that transaction, and if you are able to go level up and reach the Merkle root, and if the Merkle root is same, you know that that transaction is part of that particular block. So this also becomes easier, right? So this Merkle tree, this is all called Merkle tree, and there are multiple uses of this tree in various searching functions which are there, which is out of our scope, but you can go ahead and learn more about it, right? So there are a few other examples, other references that professor explains. So let me go ahead and share it with. So the structure of the Merkle root is always going to be as a tree, and this tree is called a binary tree because every time we're using clubbing two together. So this also this Merkle tree is a binary tree, right? So this is what we have understood. So I'm just going to share, go through this image on what is happening, right? So we have gone from each of these steps. So I'm going to run through. So what is the Bitcoin transaction life cycle, right? So now what is happening is here is, so now the person Rob is trying to send some Bitcoin to his friend Laura. Okay. So now Rob, first he does is opens his Bitcoin wallet and he scans or enters Laura's address, then fills in the value, right? So if you remember in output, we are talking about value. So the value is entered and then clicks on send. So now what happens is, till here, the user did his part, and then now it goes onto the network, right? So now the wallet signs the transaction using Rob's private key, right? So this was secured by Rob's private key. Because we have understood, we have gone into the details of it. Now we are going abstract, we are going on the overview of it, right? So each of the sessions we have understood each step, right? So we have understood how a wallet address was created, how transactions are structured, and how the verification happens by the script language, right? So we are going a little abstract, a layer up above, and trying to understand what is happening. So now the wallet, whatever Rob was using, signs the transaction using Rob's private key, right? So now this goes into the memory pool, right? So whenever a transaction is done, it immediately does not get validated. It goes into the memory pool, right? So the transaction is propagated and validated by the network nodes. So now what are nodes? Are individual computers or people who are trying to solve the cryptographic puzzle, meaning try to validate that particular transaction. So it will take some time, and if your transaction has a higher value of Bitcoin, the incentive for the miner is also high. So for that reason, those transactions go faster, and if yours is a very small transaction, it might take a little more time, but then your transaction from memory pool enters, it gets validated, and the miner includes that transaction in the next block to be mined, right? So he does that, right? So if you followed the steps that we have, all the steps till here, type U in the chat box if you understood how all the previous concepts are connecting together. So if you understood all this, thank you so much, Aniket. Right. So now we have, the miner includes the transaction in the next block to be mined, And then the mining is happening. So the mining is nothing but the computational process of calculating a certain hash, right? So that process is happening, and new blocks are getting created, right? So the new blocks get created whenever a set of transactions need to be uploaded. So the miner who solves the proof of work. So we'll understand what is proof of work in our upcoming sessions, but it is good to have the overall picture. So then a miner who solves the proof of work propagates the new block to the network, right? So we have understood that miner propagates the new block to the network, but we'll understand proof of work as we proceed forward. And the other nodes, see all of the other nodes. So the one miner uploads it, right? So here one thing that was not mentioned is there are many people who will compete to verify it, right? So there are a lot of people who try to verify the transactions, and the first person who verifies the transaction and creates that particular block gets the block reward, right? So that is what we have discussed previously. The miner who solves the proof of work propagates the new block to the network, and he gets the block reward. The all other rest of the nodes, right? They don't actually actively have to go and verify, but what happens is whenever new block gets created, all the other blocks start verifying it, right? After 6 blocks being confirmed, like 6 confirmations come, more 99.99% the block is verified, right? So the block height gets added and this block gets connected onto the blockchain, right? So then now after all this process, now Laura sees the first confirmation, right? So when one verification happens, Laura sees confirmation, and as time progresses and new blocks get added, new confirmations appear onto that particular block, right? So if you see our block 4999999, if you see this, you can see that in here there is something called confirmations, which means like there are 2,78,650 confirmations, meaning there are 2,78,650 more blocks over this, right? So now if you see the depth and the confirmations are same, meaning the top block which is mined today or now, from that particular block, this 4999999 block is 2,78,650 blocks below, which is also called depth or height of that particular block, right? So those many confirmations happen, right? So whenever you see new block being added, the previous blocks get more and more confirmations and they become more and more permanent. So this is what we've understood in the whole blockchain transaction cycle, right? So if now the whole picture of how the transaction happened is clear, and type C in the chat box. So the link to the same is being shared. Thank you, Sharayu. Thank you, Janak. Okay, so you can also go ahead, and if you see in our previous transactions, like in our previous module, I keep saying transactions, in our previous modules, we have seen from the beginning, we have first understood the evolution portion, then we have understood the basics of hashing, like what is hashing before we get onto the blockchain. So you understood the compression functions, we understood the elliptic curve, and the essentials of it, digital signatures, all of those things we've understood. And then we have understood wallets. And from that wallets, we have understood this whole map in a detailed way. But now that we have understood each of the block, as we go forward, more and more things become clearer, right? So we've understood the keys, each of the nodes, then we understood each of the transaction, the inputs and outputs, how many bytes each of it is, and how are they verified onto the stack, the blockchain script language. We have understood all of that. And in the module 6, which was yesterday at the previous session and today's session. We've understood different type of nodes, the whole memory pool, and whole of the Merkle root and individual sizes of that particular transactions, right? So we've covered all that. So let me just check if there's anything that we've added that needs to be discussed here, right? So the nouns portion, which we discussed here, it's a very smaller element that we will add it onto our upcoming session, right? So rest of the other elements in the block header are clear, right? So they are time, the number of bits, the Merkle root, the previous block hash, the version. These are all clear. And the nouns we'll discuss, nouns and bits we'll discuss in our upcoming session. So one important thing is all of the block headers are going to be of 80 byte size, right? So now if you sum all of these bytes, which is 4 plus 32 plus 32. Okay, I'm just going in the traditional format. Okay, so if you go ahead and do it, plus 12, so see that it is 80 bytes. I hope my screen is visible. Okay, it's not visible. So, yeah. So now if you just sum all of them, it will be 80, right? So it will be 80 bytes. Yeah, so that is one other important information that we had to discuss. So in today's session, we've understood block header, what consists of block header, and a few concepts of the each of the elements, right? So we also understood the Merkle root, and if at all you want to understand the previous block hash, right? So it is double hashed using SHA-256. So whatever previous block hash was there, of that you're going to twice hash it and that block hash is added here, right? So the hash pointer, okay, sorry, my slide is moving. Just let me stop and share the screen again. Yeah. So now if you see each of these hash pointer is first, for example, whatever is the hash, that is first, that will go through the SHA-256, and whatever output will be there, it will be again going through SHA-256, and that hash will be added here, and that is where it comes within 32 bytes, right? Because the actual hash will be 640 bits. Now SHA-256 makes it 32 bytes. So these are a few things about block headers. I hope this session was helpful in understanding more about the block header, right? So this concludes our today's session. If there's any query, you can go ahead and ask. And even today or in our previous sessions also, that is fine. So if there's any query, you can let me know. If everything is clear, you can type U in the chat box. People who are using our social channels, you can type in the comments or chat section. Thank you. Thank you, Janaki Ramsar. Thank you, Prashant. Thank you, Suji. Okay. So if there's any other query, so people who have recently joined, I have told you on how to go forward. So this is where today's lecture is, but I would request you to start from the beginning. And as we go forward, you can go ahead and take the quiz, because that will help you in clearing the NSEM certification exam. Yeah, so Sharayu asks, when Merkle tree contains odd number of transactions, how the duplication of the transaction takes place. So, okay, so let me just paste it for everyone. So now the Merkle root is there. So it is not going to be manually calculated and uploaded. So there's a system like how we were seeing the check signature, right? So we have seen in detail about the elliptic curves and everything, but there is only one function which is going to do all of that, right? So match the public key with the secret key and all of this. So this is part of that particular system only, right? So you don't have to actually do it. So the duplication happens automatically. So this is how we have seen the duplication happens whenever there's an odd transaction. This by itself within the system takes place. Right. I hope that is clear. So you're not going to actually manually calculate and upload it. So this is happening directly and getting added onto the Merkle root of that particular block header. So there are n transactions in that block. Out of all the sequence of the transaction, the Merkle root is created and added. Thank you. Thank you, Sharaya. Okay, so I hope the session was insightful, and we're going to see more of the module 7 and a few portions that are essential from module 6 in our Thursdays hackathon. Okay, thank you so much, everyone. Thank you, Janakram sir. Thank you, Sanket sir. Thank you, Sharayu, Jay Ganesh sir, Ravindra sir. Thank you, Srinivas sir. Okay, so I hope there are no other queries. If there's any, you can always reach out. Thank you so much. Thank you, Sharayu.